In this video, we're going to look at composition of functions. So composition of functions, we're going to look at how to compose them. No. In this video, we're going to talk about composition of functions, how to compose functions, different notations for composition of functions, and then we're also going to look at inverse functions. We're going to look at what they are, determining if we can have an inverse, how to find an inverse, and how to find the domain and range of an inverse function. So let's get started with composition of functions. So almost all the functions we've ever used can be considered a composition of two or more functions. When we think of y equal to 2x plus 3, that's a composition of y equals 2x and y equals 3. It's a composition of those two functions. The different notations for composition take on these forms. We have where the two function names are together, fg, and we pronounce that f of g, f. The different notations for composition of functions, we have where the names are together, fg of x, and it doesn't have to be f and g, it could be any letter. We have the over parenthesized version. That's this one, where you can clearly see that g of x is inside of f of x. And then we also have fog notation, which is this, where there's an open circle. That's f of g, or fog notation. All that composition of functions mean, all three of these, f, g of x, means that the input into g of x is x. You're going to take that output, and that is now the input into f of x. So what that means is you first do g, then do f. So for example, let's look at x, g of x, and f of x. If we look at them as three separate functions, say x is 2, and g of x then becomes 5. For f of x, we don't put 2 in. No, we put 5 in. Let's say we get out 10. So that's how that works. I think this will make more sense when we see an example. So let's work through this example here. So there's two different ones. And I'm going to do the first one the simple way, and then I'm going to do the second one a little bit more complex. So this first one is POQ, which we can write as P of Q of X, or simply as PQ of X. What that means is we're going to take Q of X, and everywhere we see an X in P, we're going to put Q of X. So we start with P of X. So we have x squared plus 6. And Q of x is the square root of x plus 9. So P of Q of x means take Q and put it into P. So everywhere we see an x in P, we're going to replace it with the square root of x plus 9. So PQ of x becomes square root of x plus 9 squared plus 6. And we can simplify to x plus 9 plus 6, or x plus 15. Okay. So we've done the composition, and it says to evaluate it at 7. So we're going to plug in 7, and we're going to get 24. 2. So P of Q, how do I want to write this? PQ of 7 is equal to 22. So that's how you do the composition of functions. The other way to do it is when you're just evaluating, like this particular problem is asking for, you don't have to do this that I did right here. We can simply do, so we're looking at QP of x now, but we're not looking at QP of x, we're looking for QP of 7. So we put 7 into P. So P of 7 is 7 squared plus 6, which is 55. So 55, instead of Q of x, we have Q of 55. 55 plus 9, which is 64. And then the square root of 64 is 2 and 32, 2 and 52, and 16, which is 4 times 4. So the square root of 64 is, I should have known this, is 8. So that's your solution to the second one. Hopefully that gives you some idea about the composition of functions. This first way that I showed you here in yellow is where we actually did the composition of function and then evaluated. Here in blue is where we kind of evaluated as we went. Both are valid methods if you're actually looking to evaluate the function, like they are here where it says find when 7 is x. Now we're looking at the domain as well, and the domain of the composition specifically. So it says, so what we're looking at is f of g. So we're first going to do g and then do f. So looking at f, everywhere that x is, we replace it with g. It's going to be 2x plus 1 plus 2, 2x plus 1 minus 3. So 2x plus 3 over 2x minus 2. And now we're looking for the domain. So the domain of f of g of x. This can get somewhat complicated, but simply we're asking for, what it's asking is we look at our composition function here, and what are all possible input values? So what are all possible x values? So if we look, x can be anything except x cannot equal 1. Because if x is equal to 1, the denominator is 0. So what we say is x is contained within all real x not equal to 1. So that is your domain. We could also have written it as domain we could have written it like that. And we also could have written it as an inequality. So there's a couple different ways. Now we're going to look at inverse functions. So inverse function undoes the action of a function. So for example, If a function adds 1 to the input, then the inverse is going to subtract 1 from the input. Okay. Well, I think it'll make more sense when we see examples. What's important to note about inverse functions is this part right here, domain and range of inverse functions. So domain of f of x becomes the range of f inverse of x. And then the same is true for the range of f of x becomes domain of f inverse of x. That will come into play and will be very useful as we go through this section. Now, the different notations, the notation for inverse is usually the -1. Okay, you've seen that before with sine, cosine, and tangent, hopefully. SOHCAHTOA. If not, we'll get to it in a couple of lessons. So, but the inverse exists if and only if, this isn't a typo, that means if and only if, the function is 1-to-1. So remember earlier in this unit we talked about what a 1-to-1 function is, okay? And the way to test if a function can be inverted without special considerations, you do the horizontal line test. So recall the vertical line test tells us whether or not something is a function. The horizontal line test tells us if we can take an inverse. So let's take two different functions. Let's take this function and this function. And then let's perform a horizontal line test. So if we move this horizontal line up and down, we will only cross this function once. So this one has an inverse. Now if we do the same thing here and move this horizontal line up and down, we are going to cross at 2 points. So this one has no inverse without restrictions. And we'll look at what that means here in a second. Okay, here's a little more on the horizontal line test and more on those restrictions. So if we think about the function we were just looking at that failed the horizontal line test, our good old quadratic equation, it fails the horizontal line test because it has two solutions. However, if we restrict the domain so that we are only looking at the left or the right, recognize I said backwards from what I drew, then we can take the inverse function. Graphically, this is what an inverse function, any inverse function is it's a reflection across the y equals x line. So if you think your y equals x line, your dotted line here, you can reflect any function across that line and get its inverse. We don't do a lot of inverse graphically beyond just the abstract understanding. So how to find an inverse. Here's where the tips and tricks in all of the algebra that we've been practicing come into play. So to find an inverse function, you solve for x. Then once you solve for x, you swap the variables. You swap x for y, and then you call it your inverse function. Then if there are any domain restrictions that you need to put on it, that's the last thing you do. So let's look at our function that we're given here. So the first thing we're going to do is we're going to get rid of f of x, and we're going to call it y. Sorry, Luke is playing with his squeaky toy in the background. Now we're going to solve for x. We need to isolate x. Okay, we're going to put x in quarantine. So we're going to subtract 10 from both sides. And then we're going to cube it. And then, so we've got y minus 10 cubed minus 6 equals x. Bingo. So we've now isolated x and put it in quarantine. So our next step is going to be to flip them back. So we're going to say y equals, and this is going to be equal to f inverse of x minus 10 cubed minus 6. Now, the reason inverse function works is this and what they're used for. So let's work in purple. So let's say if x is equal to 2. So we're going to evaluate f of 2. So we end up with the cubed root of 2 plus 6 plus 10. This gets us 12 because the cubed root of 8 is 2. 2 plus 10 is 12. So the inverse function will work and is correct if we take this 12, put it into our inverse function, and we get back 2. So let's check and see. So f inverse of 12 equals 12 minus 10 cubed minus 6. So let's see, 12 minus 10 is 2. 2 cubed is 8 minus 6 gives me 2. So there we go. That's your full circle. That's your test to know whether your inverse function is correct. Okay, here's another one that we're going to look at together here. So again, y equals square root x plus 1 minus 6, y plus 6 plus 1, y plus 6 squared equals x plus 1, y plus 6 squared minus 1 equals x. So f inverse of x is equal to x plus 6 squared minus 1. Now, for the domain -1 to infinity, so that domain's already given to us. So there we go. A couple for you to try in class on your own. So in this video, we looked at composition of functions, what they are and how to compose them, different notations for them, and we looked at inverse functions, what they are, determining if you can have an inverse, how to find an inverse, and the domain and range of inverse functions.